Welcome to học tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, A History of Science in 100 Experiments. Today we will read story number 63, A Ruler for the Universe. You might think that measuring the size of the universe is an impossible task, beyond the scope of any experiment or earthbound observations. But between 1908 and 1912, an astronomer working at Harvard College Observatory, Henrietta Swan-Leavitt, discovered a way to measure the distances to certain key stars, providing a ruler to determine distances across the universe. Leavitt was carrying out a survey of stars that vary in brightness. These variations may happen because the star actually does get brighter and dimmer as time passes, sometimes with a regular cycle, or because it is simply a binary pair where one star gets eclipsed at regular intervals as the other star passes in front of it. By this time, astronomers no longer had to rely on their unaided eyes, and she worked with the photographic plates containing images of thousands of stars in the southern skies observed at different times. After many hours of painstaking analysis, Leavitt noticed a pattern in the behavior of certain kind of star in a large concentration of stars known as the Small Magellanic Cloud, SMC. The family of stars known as Cepheids had an overall pattern of behavior in which the brighter stars, taking the average brightness over the whole cycle of brightening and dimming, went through the cycle more slowly than the fainter Cepheids. By 1912, she was able to work out this period luminosity relationship in terms of a mathematical formula based on the measurements of the variation of 25 Cepheids in the SMC. She realized that the patterns showed up because the SMC is a cloud of stars so far away from us that the separation of the stars in the cloud is small compared with the distance from the cloud to us. So light from all the stars get dimmed by the same amount on its way to our telescopes. For nearby stars, it is hard to tell if one star looks brighter than another because it really is brighter or because it is closer. But as the variables in the SMC, quote, are probably as nearly the same distance from the Earth, unquote, she wrote in 1912, their periods are apparently associated with their actual emission of light, as determined by their mass, density, and surface brightness. Leavitt found that, for instance, a Cepheid with a period of 3 days is 1/6 as bright as the Cepheids with a period of 30 days. But these were all relative measurements. Astronomers still needed to measure the actual distances to a few nearby Cepheids so that they could work out their actual absolute brightnesses and use these to calibrate the distance scale. Once they knew the distance to one Cepheid, then they could work out its absolute brightness. And using the relationship Leavitt had discovered, they could then work out the absolute brightnesses of other Cepheids, so their apparent brightnesses on the sky would reveal their distances. The first such measurements based on various techniques that only work for nearby stars were made in 1913, but they were somewhat inaccurate. Modern measurements imply a distance to the SMC of 170,000 light years, so that even if two Cepheids in the cloud are 1,000 light years apart, this represents only 0.6% of their distance from us. In the 1920s, surveys were used first to measure distances across our Milky Way galaxy and determine its size, then to measure distances to what turned out to be other galaxies beyond the Milky Way, showing that the Milky Way is not unique, but just an ordinary island in space, one of hundreds of billions of such islands in the observable universe. It was by using surveyed distances for galaxies that Erwin Hubble was able to work out the relationship between the redshift in the light from a galaxy and its distance, leading to the discovery that the universe is expanding and to the idea put forward by Georges Lemaitre, who independently came up with the redshift distance relationship of the Big Bang. Over the decades since the work of these pioneers, other cosmic distance indicators have been developed, most notably certain kinds of supernovas, stars that all explode with the same absolute brightness. But we only know the distances to the X-tipo supernovas used to calibrate this part of the distance scale because they occur in galaxies whose distances have been measured using surveys. This is so important that developments of Leavitt's work continue today. The Hipparcos satellite, launched in 1989 by the European Space Agency, measured accurate distances to more than 100,000 stars, including 273 surveys, using geometric techniques. This provided the most precise calibration of the cosmic distance scale in the 20th century. But a follow-up mission dubbed Gaia was launched in 2013 and should provide even more accurate measurement by 2020. More than 100 years after Leavitt's discovery, developments from her work continue. Now to the vocabulary section. Impossible task, brighter, dimmer, eclipse, solar eclipse, lunar eclipse, small Magellanic cloud, luminosity, emission, surfeit, calibrate, inaccurate, inaccurate, unique, unique, observable. The verb is observe, observing, observable. Redshift, pioneers, pioneers, supernovas, geometric techniques. Thank you so much for your time, and as usual, I will see you in the next story. Bye for now.